So hello everyone, my name is Xingyu. I'd like to talk about our performance paper on load balancing heterogeneous servers with multiple dispatchers. This is a joint work with Professor Ness Shroff and Professor Wierman. Load balancing has been becoming a key component in nowadays cloud computing systems. For example, let's consider the image classification task. This image will first go to one particular cluster, and within each cluster, it will go through each layer load balancer. So in this talk, we'll focus on the last layer called layer 7 load balancer. From this picture, we can see that there are two fundamental features. First, there are multiple dispatchers, and also there are a large amount of servers whose service rate may be different. We call heterogeneous servers. We are interested in the following questions. First, with multiple dispatchers, does Zhou queue still beat others in performance? So we know that for the single server system, Zhou queue have been shown to have optimal performance in a stochastic order sense compared to others. But unfortunately, in the multiple dispatcher cases, due to the herd behavior, means that at the same time, all the arrival at different dispatchers will join the single shortest queue. This will hugely impact the performance. It leads to a very poor performance actually. So how can we avoid this situation? Second question is, can each dispatcher work independently with simple implementations? How much communication do we really need between dispatchers and the servers? Because we have multiple dispatchers, we want to minimize the message overhead between the dispatchers and the servers. And last one is, can we say something about the performance guarantee? So how about the stability and or even delay? Here is our result. So we propose a new design framework called LED. So it's named after local estimation driven. So it has three components. The first one is memory. Each dispatcher has a local memory which stores its own local estimates of each server's queue length. And the second component is dispatching. So the dispatching decision at each dispatcher is made purely based on its own local memory. Updating. So the local memory will be updated once a while via the messages or communications between the dispatcher and servers. By updating, we mean that the dispatcher will synchronize the local estimates with the true queue length. We have derived the sufficient condition on the dispatching and updating strategy to guarantee supernormality and delay optimality in heavy traffic. Our proposed LED framework combined with the sufficient condition also shed light on the recently open problem on load balancing with delayed queue length information. As you can see, LED framework can include a lot of policies. Let's look at one concrete example. First part, memory. So each dispatcher has its own local memory, which stores its own local estimates. We consider one particular dispatching strategy called local joint queue. So each dispatcher will independently route new arrivals to the server with the shortest local estimates. For example, in this case, dispatcher A will route new arrival to server 2. And on the other hand, dispatcher B will route new arrival to server 3. Updating. So we consider one particular push-based updating strategies. Basically, it means that each dispatcher will independently randomly sample D servers. In this case, D is equal to 1. Dispatcher A randomly samples server 1, and it will synchronize the true queue length to its local estimate. If we look at the related works, previous load balancing in multiple dispatchers either consider homogeneous servers or homogeneous nodes across different dispatchers. Load balancing with memory has been becoming very popular these days. A variety of policies has been combined with local memory to improve the performance, but all of them only consider single dispatcher. Maybe the most related one is a recent work. In this work, the authors consider one particular dispatching strategy, i.e. the local joint queue. More importantly, they only consider the stability, while we also touch on the delay. So look at our model carefully. We have M dispatchers and N servers. And the arrival process is integer valued at each time slot t and ideal across time slots. We assume that there is strictly probability such that there is some arrival at each dispatcher M. And the service process is also integer valued ideal across time and an independent arrival and queue length. We use tilde queue to denote the local estimates. we care about two metrics, supernormality and denormality in heavy traffic. We use epsilon to characterize the distance of a rivalry to the capacity region. By supernormality, we mean that for any epsilon larger than 0, though, the system is positively recurrent and the moments are finite. By heavy traffic denormality, we mean that as epsilon goes to 0, though, in this heavy traffic, the sum Q length will converge to the resource pooling system. Before we present our main results, let's first introduce one notion called dispatching preference. For it, we first do a permutation of the local estimates, and then we define probability PMNT as the probability of routing to server N at dispatcher M in time star T. The preference of the N's shortest local estimates at dispatcher M is given by this term, so it's a difference between two probability. As you can see, if the delta MNT is larger than 0, it means that this particular policy has a stronger preference of the N's shortest Q, or N's shortest local estimates compared to the random routing. And we can also note that the summation of the delta term is equal to 0. So the question is, how can we allocate the zero sum? We want to allocate more positive values to the shorter local estimates. This naturally leads to the following condition called delta tilted sum condition. So for any j between 1 and n-1, the first j sum of the big delta is larger than or equal to a small delta. The intuition is very simple. So for any first k shortest local estimates, the total preference is at least a delta. If we look at the three server examples, so we suppose the service rates are equal, and we consider one particular local estimates state. So for this particular state, the delta tilted sum condition will be satisfied for any vector p if the following three equations are satisfied. As you can see, there is a much flexibility here. And this condition and this flexibility directly generalize previous conditions in our previous papers. And by this generality, we can establish new results. Here are our main results. First, stability and supernormality. So we use the indicator function IMNT to indicate that server N's Q length is updated at dispatcher M. So consider any AOD policy if the dispatching strategy satisfies the delta tilted sum condition, and the updating strategy satisfies this condition, which means that there is strictly positive probability such that for any system state, the server N's Q length can be updated at any dispatcher M. Then this policy is supernormal optimal. For heavy traffic denormality, it actually requires slightly stronger conditions. So the dispatching strategy should satisfy with a strictly positive constant delta, and the updating strategy should satisfy with independence across different updates. And both the delta and p are independent of epsilon. This directly implies that there is a large class of AD policies that are heavy traffic optimal, which definitely includes the specific one in the previous paper. And moreover, we should note that a single server with adequate Q length information is just a special case of the AED framework. Let's look at some examples of less dispatching strategies. First one is local join short queue. So it will always join the server whose local estimate is the shortest one. And it can be easily checked that this strategy satisfies the delta tilted sum condition. Instead of always joining the shortest local estimates, maybe we can join any servers whose local estimates is below the average. And for this particular one, we actually require the dispatcher have the knowledge of the service rate, but it can be easily obtained via the communication between the dispatchers and the servers. Maybe more interesting one is the local POV-D. So randomly, for each dispatcher, randomly sample D servers and join the one with the shortest local estimates among the D servers. In general, POV-D has been shown to be unstable for heterogeneous servers, but by using the delta tilted sum condition, we can show that as long as the heterogeneity among the servers rate satisfies this condition, the LPOD policy or dispatching strategy satisfies the delta tilted sum condition, and as a result is superoptimal and heavy traffic data optimal in the heterogeneous servers and with multiple dispatchers. So for the particular case, this paper also established some similar conditions. Let us turn to the less updating strategies. We can characterize into two aspects, push-based and pull-based. For push-based, each dispatcher will take the initiative to sample servers. For example, with a certain amount of probability to randomly sample one or more servers and synchronize their queueness. It can be easy to check that this condition will be satisfied with this probability. On the other hand, pull-based updating strategy means that each server will report its queueness to a randomly sampled dispatcher. If it is idle, it will report with probability 1. Otherwise, it will report with a certain amount of probability. It has been shown that for arbitrarily small probability, this condition can be achieved. So let's go back to our motivating questions. Zhou queue in multiple dispatchers. How can we avoid the herd behavior? The AOD could be one possible solution because due to its intrinsic randomness. If we look at this problem deeper, we do a simulation. So we run 100 heterogeneous servers with 10 dispatchers. First, note that the poverty and Zhou queue are unstable. More interestingly, the Zhou queue with the full accurate information behave quite poorly. On the other hand, all the AED policies have good performance. Randomness can further help. So we consider this extreme case that the updating strategy is very small. So there is a long interval that there is no any update. If we use local Zhou queue, it's still very deterministic. On the other hand, if we use local POP-D, because sampling, we have some introduced randomness, and this randomness can help us to obtain a better performance. For AED, each dispatcher can work independently. And how much communication do we really need? In terms of stability and heavy traffic normality, we can show by our sufficient condition, the communication overhead can be arbitrarily small. But of course, for the practice performance, we can tune these parameters based on our trade-offs. So last one, can we say something about the performance guarantee? By our sufficient condition, we establish supernormality and delay optimality in heavy traffic for the AED framework. The main ideas behind our proof are based on the drift method. In particular, we use the sufficient condition for supernormality and heavy traffic normality developed in our previous paper. The idea can be illustrated as follows. For supernormality, we need to establish the positive drift indicated by the orange arrow. And for the heavy traffic denormality, we should establish the green drift. There are some additional challenges arise in our settings. The first one is we consider more general dispatching conditions. To the best of knowledge, this is the most general case. And this general dispatching condition even exists when the queuelines are accurate. Second one, for outdated queuelines information, we handle it by first assuming that the local estimations are correct. And then we establish necessary drifts. And finally, we try to bound the error. Third, the system states also include local estimates. So in certain near-proof drift method, we should carefully bound it. So in summary, our proposed AED framework, combined with the sufficient condition, gave affirmative answers to all the previous key questions. So it can help us to avoid herd behavior. It can enable the dispatcher to work independently, and we can achieve a certain performance guarantee with arbitrarily small communication overhead. There are also some very interesting future research directions. First one, we can go beyond the traditional heavy traffic regions. As pointed out by our previous paper, heavy traffic denormality may be a coarse matrix. We can turn to some other matrix like weighting probability in non-system regions. We can also turn to continuous time systems. Maybe a more interesting case, we can incorporate the AED framework into load balancing on graphs. In this case, each node can serve a job or maybe dispatch a job to neighbors. And each node can keep a local estimates of its neighbors. And the dispatching decision can be made purely based on the estimates. And we can update our information about neighbors' queuelines via some communications. So thank you. That's all.